This episode is with Maria Galloway-Sprietsma, an astronomy PhD student at the University of Florida, currently focusing on planet formation, early star formation, and radio instrumentation. Thank you for being here, and I hope you enjoy this episode. How are you doing today?
I'm good. How are you?
I'm doing well. Had a productive day so far, so that's been pretty good.
That's good. Me too.
Yeah.
Yeah.
Well, that's good as well. So, first of all, thank you for making time and everything. I'm sure
thank you
you've
for
been,
inviting me.
yeah, I'm sure you've been busy. I would imagine, at least, that when it comes to having or being in a PhD program, you're busy a lot of the time.
Yeah, the summer is a little bit better, to be honest. A little bit less busy right now, but
Okay.
still a lot of stuff going on.
Do you have class or no?
Not over the summer. I have 1 or 2 semesters of classes left, so I'll take those in the fall and in the spring.
Okay. When do you start school?
I think so. I'm at University of Florida, and it starts probably like mid-August. I think. I actually don't know the date. Yeah.
Okay. Yeah, I start similar. I think it's around, I want to say the 16th, 17th, something like that.
Yeah.
So it's around, I'm sure it's similar time frames.
You're at Miami, right?
Yeah. I'm Miami. I'm still in my undergrad though. I'm on my last semester now. So I'll be finishing up. I'll be graduating in December actually.
Awesome. That's exciting.
Yeah. Yeah. After that, I'm still trying to figure out what I'm doing.
Yeah.
Yeah. But yeah, I mean, I thought I looked at your profile. That's why I contacted you. I thought that your focus and everything, I think it's pretty interesting. So if you want to share a little bit about that.
Yeah, sure. So I'm a first year PhD student, or I've just completed my first year. So I'll be going into my second year. And I right now am focusing on planet formation using mostly radio telescopes. And I switched up a little bit in my undergraduate career. I did star formation and a lot of astrochemistry, which I loved. But yeah, my first year at University of Florida, I am now doing planet formation, and I'm looking at the earliest stages of planet formation. So this is a really exciting time to be in that field because we have some really big new telescopes that are able to probe these really young stars that have disks around them that are forming baby planets. And we're able to kind of see that for the first time. So I'm really interested in some of the structures that we see in these disks. We see some really cool like rings and gaps, stuff like that, or spiral structures. And I'm interested in just learning more about how planet formation begins and what that process is like. Unfortunately, not unfortunately, but planets that I technically look at or hope to find are more like Jupiter and Saturn, not really planets like Earth or Mars yet. We will need some bigger telescopes to see those. Okay,
right. I'm happy that you mentioned telescopes because I think we've all seen in the news like recently with the James Webb telescope images.
Yeah.
Before we dive a little bit into kind of more your focus, I just wanted to ask you because I don't know myself as much about it. I'm sure you do, or at least more than I do. And if you wanted to, I don't know if you want to explain a little bit about like what the news about the James Webb telescope is and kind of what it's encompassing.
Yeah, so I can talk a little bit about that. I'm probably not the best astronomer to ask about it, which is a little embarrassing, but I'm still really excited about it. So JWST is a brand new telescope that just came online and it's in space. And the first 5 images from it have just been released. And they are really, really beautiful. If you haven't seen them, one of them is a spectra, which is still really awesome. I guess if you don't really look at spectra so much, you might not know why that one is awesome. But the images are really beautiful. It imaged a wide variety of things. So it did look at a small section of the sky where we see a lot of galaxies that are being gravitationally lensed. And that image, I think it was the first one released, is one of the most exciting because it's one of the deepest images we have, and it is looking technically further back in space than we've seen before. And the light from that image is really old, and we're able to see a bunch of galaxies in greater detail than we've ever seen before. So that's really exciting. And I think JWST, a lot of astronomers, I mean, every astronomer is really excited about it because it is really applicable to almost every field of astronomy. So everyone over the next few years in astronomy is going to be able to get some really great data with better resolution than we've ever had before.
Yeah. What's the difference between that telescope and ones that we already have?
So this one, I think a lot of people compare it to Hubble, and James Webb is bigger than Hubble, I believe. So this is where I'm not actually like exactly an expert on this.
No, don't worry about it. Like, you don't have to get everything exactly right. It's
okay,
not.
Okay.
Yeah, don't worry about it.
Okay.
I just wanted to get a sense, like an overview of what it is, and I think people are excited, as you said, about it.
Yeah.
And so addressing that, I thought would be appropriate.
Yeah, no, I think so. Yeah. So James Webb is it's bigger, and basically it's bigger and better, and it'll be able to take higher quality images and get higher quality data than any telescope previously, just because of the new advancements in technology. And it'll be able to do all of that much faster than ever before. So the older Hubble images, I think some of them took about a week or so, just a week of staring at one spot in the sky and collecting light. And the new images from JWST that were released took much less time than that. I don't know exactly how much time, but that's something really exciting for astronomers, because sometimes we have to look at objects in the sky for many, many hours or days to get enough light to get good data. But this is really exciting. We can do this so quickly and with such high precision.
Yeah. Do you know how these telescopes work? Do they send, once they take a certain picture, do they send the signal back over to some space station, or how does that work?
Yeah, that's a great question. So I'm assuming with JWST, it would collect the data and then send it through like a downlink, just like a satellite exchange. But I actually don't know the intricacies of that as well. I'm assuming it's just kind of a downlink satellite process. But yeah, I don't know where that data is, because it is a lot of data. So I'm assuming it takes a bit of time to come down, and then of course a bit of time to process.
I'm curious because you mentioned astrochemistry. I don't think I've ever heard of astrochemistry before. I imagine it's what kind of processes take place in space when it comes to the chemistry of it, but I don't know much.
Yeah.
I wouldn't know what exactly it is comprised of.
Yeah, that's exactly it, pretty much. Just the processes of chemistry happening in space. So there's a lot of stuff up there, actually, a lot of chemicals. So astrochemistry is just the study of that. And there's, I would say, in each astronomy field, you could get into astrochemistry. So I specifically was doing the astrochemistry of star formation. But all the chemicals that we have on Earth and all of the molecules and stuff like that were created in space through the process of stars living and dying. And specifically what I did with astrochemistry is when stars are forming, they form out of these really cold, dense clouds that before the star forms are very cold. And this kind of allows for the creation of really complex molecules. So we can get prebiotic molecules that, if I wrote out their chemical name. They're really quite long, which means that there is a lot of chains, a lot of formation happening, and we can see those. We can estimate the amount of those molecules up there in specific clouds with our telescopes. And I think astrochemistry, I especially liked it is because, it does kind of relate to life on Earth. Like, how did life form on Earth? The answer probably starts a little bit with astrochemistry and understanding what important molecules form in space and then eventually end up on planets like ours.
Right. That's interesting. How, you started with, you said in undergrad you did astrochemistry. What made you transition from astrochemistry and star formation to then wanting to look at planet formation?
That's a good question. I've always loved planet formation. Planet formation. And I had always wanted to get into the field, but I ended up doing star formation, which I also loved. It kind of comprised the same techniques for the most part, at least from what I found. But when I transitioned from undergrad to graduate school, I wanted a little bit of a change just to see what other types of research were like. And there was a new professor at the University of Florida who had just started working there who does planet formation. And I decided to work with him and see what it was about. And I really, really liked it. The thing with astrochemistry and what I was doing specifically is that it's really hard, in my opinion. It's really hard to estimate the number, of molecules that are there. There's a lot of radiative transfer processes happening, that kind of stuff, and the math that I have to do. And so with planet formation, I found it a lot more intuitive because I'm doing more of the kinematics of it. So more like
Motion,
velocity, right? Motion, yeah, that kind of stuff. So I really liked that. A lot.
I'm sure it's very different, like planet formation compared to star formation. How does it differ?
Well, the scale of what we're looking at is a lot different. So with star formation, the scales of the objects that we're looking at are tens of thousands of AU, and 1 AU is the distance from the Earth to the sun. So these objects where stars are forming, I mean, if you zoom out, they could be, extremely huge molecular clouds. But now that I'm doing planet formation, the things I'm looking at are much smaller in space. So they're only, out to maximum like 300 AU. Right now I'm able to use some different telescopes than what I had been using previously. And I think that's really just because I'm in grad school now. So the research is a little more serious. So I'm using maybe some more serious telescopes.
Yeah. As for the chemical composition of, say, planet forming in its initial stages, is it also different to a star?
Yeah. So it's still, there's still a lot of, the base elements of hydrogen and helium. But what differs is what we're able to look for because the temperature differs so much. And so when a star is forming, particularly at the stages that I was looking at, it was very, very cold. And in some cases, there wasn't even a star there at all. It was just gas and dust that was very cold. And so now that I'm looking kind of further down the, maybe like the life cycle of a solar system, things are a little bit warmer. And so the types of molecules that are there are different. And that means that the things I want to look at to get information out would be a little different as well. So for example, right now I'm looking at a lot of 12CO, 13CO molecules, and previously I looked at things like deuterated ammonia, which is a larger, more complicated molecule.
Right. Okay. You said that the stars, they originate from was it a cold cloud? It's like I imagine the cloud is made up of a bunch of different particles and so on. Now, what is a planet made out of, or how does it originate?
So that's a really great question. In all honesty, it's a little bit harder to imagine how a planet forms as opposed to a star. So when a star forms, yeah, like you said, there's a bunch of particles of gas and dust, and they're all kind of in this very large glob, and something will perturb that glob and start to force it to collapse down, and then gravitationally, gravity will take over and it will collapse down and eventually form a star in the center. That's kind of a simplified version of it. With the planet, we're now forming things out of a disk instead of a sphere. So that's kind of the initial difference between a star forming and a planet forming. And when something is forming out of a disk, gravitationally, maybe it's not as like intuitive to imagine things collapsing down. But when we have a disk around a star, there will be differences in the pressure in that disk, and that will cause small particles to clump together, and eventually the little tiny pebbles, they're called, will stick together and get bigger and bigger and bigger until they're able to exert a gravitational force large enough to kind of really start collecting mass and then create a planet. But in all honesty, the exact process of planet formation, of how we get from tiny pebbles or in a disk to a larger planet, that is kind of a mystery. And we are still really unsure of how that exactly happens, and how planets that we see end up where they are today. So it's a very complicated process.
Why is there such a variety when it comes to how a planet can form, and kind of what materials you can find in it, what chemical components you can find in it? Like, why does it vary so much?
Yeah, that's a great question. Because, in our solar system, we have really rocky planets closer to the sun. And then we have really big gaseous planets that are further out away from the sun. And that is actually because of the ice line. So ice lines are what astronomers call different points in a solar system where certain molecules are either frozen or in their gaseous form. So, and this is all because of the central star. So in planet formation, the central star plays a really big role, not just gravitationally, but also it's heating. So it's heating this disk where these planets are forming at. And so this heating makes it so that planets that are forming closer to the star will only be composed of more rocky materials, like how Earth is made of, or how Mars or Mercury, because lighter gases, like things like hydrogen, helium gases, things that Jupiter are made out of, will be able to escape because they're heated up so much from being close to the star. So that's why planets that are further away are gas planets, because that gas wasn't able to escape because it wasn't hot enough, and planets further in are much more rocky.
Is it always the case that the closer planets, like say you go to any other galaxy, and you look at the planets that are in near proximity to the star within that solar system, what is it always the case that you can go into those near to the sun planets and kind of get into, or get off technically into the rock? Because I know that if you go to a gaseous planet, there's nowhere technically where you could actually get off, or an astronaut could get off. Would it be possible in these other situations does the rock being there allow for people, I guess you could say, or some sort of life or something to form in it?
Yeah, so as far as I know, there are not, I think maybe the first part of your question was kind of asking if there are gaseous planets that are closer to stars. That's not like our solar system. So as far as I know, the only way you could get, a rocky planet really far out or a gaseous planet close in would be some kind of like event in the solar system. But I also, to your other question about being able to like stand on the surface of the planet. So you wouldn't be able to stand on the surface of Jupiter or Saturn, as far as I know. Well, there'd be some issues before you really were kind of deciding whether you were standing or not. So I think maybe at some point, let's say you're an astronaut and you fly to Jupiter and then you get off your spaceship, I think you would fall for a while. And then if you somehow survived, which you wouldn't, the atmosphere would probably become so thick that I think you would just stop falling at some point. And then Jupiter does have a core made of more rocky materials, of compressed materials, but I don't think you would reach that. I think you would get stuck kind of in the atmosphere.
That's interesting.
Yeah.
So I always had the idea that, when it comes to our solar system, Jupiter is a good example. We know that Jupiter is a gaseous planet. I always had the idea that you could, imagine you're in a spaceship, you could just like go through it. I know you couldn't because it would be toxic and so on, but like there wouldn't be anything solid in the middle of the planet. And now that you say that, there is, I think that's interesting.
Yeah, there is. I believe it's made of, iron and nickel, and also compressed hydrogen and helium. It's an interesting thought experiment, though. I think that even the atmosphere of Jupiter would kind of stop your spaceship at a certain point.
That's something else that I was that you said that I found interesting. How could it be stopped by the atmosphere? Is it, you said that it gets thicker? Like what can we compare it to that we know of?
So this is my speculation.
Okay.
But I think maybe I would compare it to, I want to say honey or something really viscous. I know honey is more of a liquid. So I might be wrong, but as far as I understand, I don't think a spaceship would be able to go all the way through. Like if you're so let's say like Jupiter's here and you went through the top of it, I don't think you'd be able to get all the way through if you were down a certain ways, just because the atmosphere is so thick. And the way I was imagining it was, the atmosphere would be kind of the consistency of honey, or I think it would just be so many hot, dense particles that at a certain point it would be impossible to get through. But
what are these?
I'm not sure.
Sorry, Mike. What are these particles made out of? What's the chemistry behind it, I guess?
Yeah, so I think for Jupiter, it would be mostly hydrogen and helium again. But then Jupiter also, has that great red spot and some really beautiful clouds if you look at images of it. And those are made of sulfur and I want to say nitrogen as well. So sulfur and nitrogen. And then trying to think of, it's definitely an array of chemicals, but I know Jupiter has some sulfuric clouds, nitrous clouds, and I believe there's also some water clouds on Jupiter as well.
Okay.
Yeah.
And when it comes to these rocky planets versus these gaseous planets, when you have the further away from the star planets, which are gaseous, they still, like between themselves, they're still different. So if you take Saturn, it's very different to Jupiter, and it has, I'm sure, different qualities to it. And then if you see Mars and you see Earth, they're very different as well. But what makes these changes happen?
It's a great question. So a lot of it has to do with the position in our solar system that the planet originally formed. So for example, Mars is a little bit further away than Earth from the sun. And so, like I said before, the distance from the sun plays a role in what kind of atoms and molecules are on that planet. So that's one of the reasons that those differences happen. Another reason is definitely the size of the planet. So Jupiter is a lot bigger than Saturn, which probably means that when Jupiter was forming, it was able to collect a lot more of the close by material than Saturn, and Saturn may have formed after Jupiter. So that would affect the composition of the planet. And then for things, for the terrestrial planets closer in, having an atmosphere can also really change what's happening on the planet. So Earth has an atmosphere that allows us to live here, But Venus has an atmosphere that is so incredibly thick that it doesn't let sunlight really penetrate, or sorry, it doesn't let sunlight get to the surface, and then it begins to heat that planet up, kind of like a runaway greenhouse effect. And so slight changes in, the distance that the planet is from the star and slight changes in the size of the planet can create a huge difference in what actually happens to the planet.
Yeah. At what point during the planet formation process are these kinds of things defined? So, for example, with atmosphere that you mentioned, at what point is the atmosphere made, and kind of why? Well, you mentioned why, but at what point are these changes, I guess? When do these changes take place?
That's a great question, and I don't know the exact answer. I definitely have been studying planet formation at a much earlier time than anything where it would have like a stable atmosphere. But I think that it kind of depends on the time it took for the planet to form. But then also, once the planet is formed, there's a long period, I think, where it could have an atmosphere, and then the atmosphere could dissipate or disappear. I'm not an expert on Mars at all. I actually don't know much about Mars, but I believe that Mars once had much more of an atmosphere than it does now, and that has kind of dissipated. And then Earth's atmosphere also changed over time. But I don't know exactly, when astronomers say, oh, this is this is the moment when like planet formation has stopped and it is now a fully formed planet.
Okay.
Yeah,
Right.
that period of time is actually probably pretty hard to observe with our telescopes that we have today.
Okay. So when it comes to the development of the planet, I'm sure it's very intricate and detailed, and it's not necessarily easy to explain quickly when it comes to narrowing down every single part of the development of a planet, right? But if you could, I guess, give an overview of kind of the different stages of planet formation, at what point does the atmosphere, like you said, start to develop, or when do the rocks in the rocky planet start to form, like those kinds of things?
Yeah, I'll try to answer this in the scope of what I do. I'm still
Okay.
new, and what I study right now is giant planets that form. So in the planet formation process, we start with a disk that is full of gas and dust that is orbiting a central star. And at this point, the system is very young. And from what I understand about planet formation is that one of the first things that happens in this disk to start a planet forming is that tiny little pieces of the material start to stick together. And these, again, form those tiny, tiny pebbles. And these pebbles might be situated in a specific ring around the central star. So I would say one of the very first phases is pebble formation. Second stage would be pebble sticking together phase, where somehow we hope that the pebbles are able to collide and then stick. And so the process of these pebbles colliding and then sticking is actually another thing that is really hard to model and understand, because there comes a certain size where if the pebbles collide together, one of them is statistically likely to be big enough to just break apart the other pebble. And so in planet formation simulations and in real life laboratory tests, it's kind of hard to simulate this phase of planet of pebbles sticking together. But we do know that pebbles stick together because there are planets. So eventually the pebbles are able to stick together enough to form a larger core. And at this point, I think the core starts exerting more gravity in its orbit as it goes around. And at this point, more and more material begins to be picked up and accreted onto this planet. this baby planet. So this would be another phase where there's probably likely no atmosphere, and the aspect that I'm talking about is there's only one planet at this point. And so I think a lot of research points to there being the formation of one giant planet in the disk, which is kind of what I was talking about. And then that formation of that giant planet allows for instabilities in that disk that make other pebbles at different locations begin to stick together and form other planets as well. So in the planet formation process, which is, I would say, something that still needs, a lot of research done on it, because we don't fully know the entire process of how this happens. One of the first things that, from my understanding, needs to happen is that one planet needs to form first to help other planets form as well. So once that planet forms, this is where I kind of deviate from my small little research expertise. I don't know at the timeline exactly for when an atmosphere would be formed and at what point the other planets are forming at. So it's a kind of an interesting question to think, like, was Jupiter almost fully formed when, Earth was just a molten liquid lava baby? That's something that I would need to read up on, is the timeline of if we're using the solar system as an analogy, the timeline of all of that.
Yeah. For being a first year, you seem to know quite a bit.
I think I've said some things that are like probably scientifically incorrect. So I wouldn't go that far.
Well, I mean, you everything you're telling me, I'm guessing that you might have had some sort of not necessarily research, but just looked into these things before maybe you started your graduate degree, I'm guessing.
Yeah, I did my undergrad degree in astronomy and physics.
Okay, so I'm sure you learned a lot of things there.
Yeah.
Where do you see kind of, I guess, how long do you have left of your program, and kind of where do you see yourself after it?
It's a great question. I have 5 years left. I think with astronomy degrees, they kind of vary from 4 to 6 years. So I think where I am right now, I have 4 to 5 years left. And then after my degree, I really enjoy astronomy, and so I hope to become a professor one day. And so in astronomy, usually the next step after you get your PhD is to go on to a postdoc or a postdoctoral degree, where you do research at a different institution for about 2 years, 1 to 2 years. So that would be the immediate next step, is to do a postdoc. And then sometimes people do 2 postdocs, so maybe another one. And then after that, hopefully I would be able to get paid to do research, or I also love teaching, so get paid to become a professor or a teacher.
What paths can an astronomer take if it's not necessarily research or teaching? Are there some sort of other paths, like job-wise?
I would say so. I think astronomers, if you are studying astronomy, you're exposed to a lot of data science. So I think some data science jobs are definitely astronomer friendly. I also did a lot of engineering in my undergrad. So I think going into the engineering field is a pretty common step for astronomers, especially ones that work on telescopes, and computing as well, or programming. Most of my job is just sitting at my computer and programming, and that's the case for a lot of astronomers. So I think that's a pretty common career path as well.
What do you mean most of your time? Like, what do you mean by spending most of your time programming?
So a big part of astronomy is running simulations and running codes. And I mean, a lot of what I'm doing is actually just making plots so that we can look at our data. But I do observational astronomy, so I take real observations, and the first step of that would be to get the data on your computer and then mess with it in some way to make it look nicer. So that's a big component. And then once you have your data, there are a lot of, depending on your field, a lot of different things that you'll want to do with it. But I would say almost every astronomer, once they've looked at their data and decided how they want to analyze it, a lot of us spend most of our time making plots as well, and then writing up that our discoveries all on our computer. So there's a lot.
So when you take the observations and then you put them into, you said to like make them look nice and stuff like that. Do you, I'm guessing to run certain simulations, there's probably some sort of software to where then you put it in and then try different things, like you said. So by programming, do you mean that you kind of, I guess, do you make or try out new software? Do you code the new software, or mostly just experiment with the data that you received?
Yeah, it depends on what you want to do in your area of expertise, but there's a lot of my peers that are working on their own software to look at their data. I'm personally not doing that because I am still not the best programmer. But one day I would like to do that. But yeah, another component of it would just be for example, I'm fitting a rotation curve to my data. And so I've fit a bunch of different rotation curves with a bunch of different parameters, and then plotted it all to see kind of how that changes what we find in the data. So there's a lot of that. Yeah.
So what programming language do you usually use, and what software is it? I'm curious.
Yeah, I use Python for everything. And I think most of my peers also use Python. And the software I'm using is, so mostly just a lot of Python packages, not anything super heavy duty. So for a specific example, one is called disk surf, which fits the emission surface of a disk. And that's by Richard Teague. So that's one I use a lot. He's actually made a bunch of software packages that I'm using to analyze almost all of my data. And I think in astronomy, usually there are so many software packages, and you could talk to anyone and they'd probably be using a bunch of different, smaller software packages that are developed by astronomers. Because astronomers do develop a lot of open source software.
Yeah. So to, I guess when it comes to programming, do you use Python to change kind of the different settings within a program to then be able to, like I said, to run these different observations in different simulated conditions? Is that what you use it for?
Yeah, that kind of stuff, definitely.
Okay.
Yeah, I know most people are probably doing wildly different things across astronomy. But yeah, a lot of the stuff, if you're not developing a software package, which I would say is more difficult, than using one, I'm just changing a few things, interpreting the data, trying to figure out what, mathematical changes to the central equation might make the fit better, that kind of stuff. And that's done all in Python. Yeah. And
then after that, then you, I guess, also observe what kind of changes take place once you simulate the conditions, or once you are able to interpret the data, and then you write up like some sort of journal, I'm guessing.
Yeah. A lot of people, just writing a paper and stuff. I would say there's a big part of astronomy where you're kind of just trying to get all your data under control, which can, in my undergrad, that took several years before I really started writing a paper. But yeah, then eventually with that data, you would start writing a paper to submit to a journal. And there's a few popular astronomy journals and stuff. Yeah.
I remember you told me that you hadn't published a paper, but you were in the process of doing so. What is your paper and research about? Yeah,
so the paper that I am first author on, that I haven't published yet, but will be coming soon, is an astrochemistry paper on star formation. It's titled Deuterated Ammonia in Star Forming Region Cepheus L1244 or 51. Kind of a long title. You don't really need to know that. But that was what I did in my undergrad. So we used a radio telescope and looked at a star forming region to better understand what kind of chemicals could tell us about its eventual evolution. And yeah, we found some interesting stuff. Unfortunately, we were kind of limited by our telescope and by the integration time, by the signal to noise that we achieved. But yeah, so that was a long process for me because it took almost all of my undergrad, and I still haven't published it officially. So it's
Okay.
kind of a long process.
Yeah, I mean, I've heard that generally, kind of like scholarly articles and papers and research take a while to publish. What's the process to do it? Like, so you do your research, you write it, and then is it peer reviewed by a lot of different people, or like what's the process?
It depends on which journal, but specifically for the one I'm publishing in, and in most of astronomy, you will submit your paper to a journal, and then there's usually one single editor that will review your paper and then give you comments back, and you're expected to like review those comments. You have a certain amount of time, and that's pretty much the process. So you review your comments, you send it back, and then depending on what journal, you can iterate back and forth with your reviewer a few times until they give you the go ahead to publish. And then at that point, which is what I'm doing right now, I'm just making some minor changes, and then I will resubmit to the journal. The changes will be approved, and then it will be out. And there's also a thing called archive, which is kind of an open source place to put your papers that you've recently published. And astronomers heavily use archive. It's very popular to have like archive coffee, where like once a week or 3 times a week, we'll all gather and like look at the new papers on archive. So
Okay,
that's a big part of it.
that's pretty cool.
Yeah.
When do you think your paper is going to come out?
I hope that it will be by the end of July or early August.
Okay.
Yeah.
And once it does, where can I find it? Where can other people find it?
It will be on archive. And I'm
Okay.
it's officially being published in the monthly notices of the Royal Astronomical Society. But it's much easier to find on archive. So yeah.
Okay. Is there anything else that you want to share? Maybe where can people find some of your research or something that you've done?
If you look up the University of Florida graduate students, I will have a picture there, and there will be a little biography about me, and it also links to my website, which will be updated fully soon.
Thank you for making time and everything. Thank you for being here. I appreciate everything. I know we certainly didn't cover every aspect of planet formation, but hopefully a brief introduction into what kind of things you look at. I think it was interesting.
Yeah, well, thanks so much for having me. Sorry if my explanations were a little confusing, but planet formation is complicated, so.
They weren't. You did a great job. Yeah, but thank you.